Hey everybody, welcome to Molecular Modeling 1. Now molecular modeling is a lot of information. We've broken it into 2 weeks for you. I'm giving it to you in bites. Make sure you reach out if you have questions. Let's get right into it. So the very first thing I want to show you. What is a Lewis structure? This is what you're looking at is what we're going to call a Lewis structure, but what is it? You also might hear it referred to as electron dot formula. And basically all it is it's 2D or two-dimensional structural formula that shows the arrangement of your electrons around atoms in covalently bonded molecules. So if you have non-metal atoms, they're going to be held together because they share one or more pair of electrons or one or more pairs of electrons. So think about the Lewis structure for a hydrogen fluoride atom. That's what you're looking at right here, a hydrogen fluoride atom. The dash between the two represents a bonding pair of electrons between two atoms. So each atom is going to be represented by their element symbol. You have hydrogen on the left and fluorine on the right. Okay, and then the non-bonding electrons that you see are going to be represented by dots, and those are going to be floating around our fluorine atom in this particular Lewis structure. So usually you have non-bonded electrons, and they pair up, and they're also called lone pairs of electrons, okay? One thing that I definitely want to bring to your attention is that when we are drawing these Lewis structures, we have one real rule that is the most important. It's called our octet rule. Now, basically, the octet rule just says that atoms bond to attain 8 valence electrons. Octet 8. Easy to remember, okay? The electrons that are shared in a covalent bond, they count toward the octet for both of the atoms that they are between. So when you're looking at this particular one, you have fluoride or fluorine atoms and a chlorine or chloride atom, and your straight lines between them means that they are bonded together. They're hanging on to each other. So our first guideline, we do have guidelines when we're drawing Lewis structures, and our very first guideline that we want to follow is first we're going to add up the total number of valence electrons for all the atoms in the molecule. So you're going to remember that your group, the number of your valence electrons is going to be your group number for your periodic table. For all the main group A elements, right, we are going to have, here we have a group, here we have a group. We're going to skip over our transition metals. We're going to focus right here on our groups, group 6, group 7, and then we have group 8. Now these are noble gases. You're not going to really work too much in the noble gases when we're doing electron dot formula. You may see it here and there, but it's not our main focus. But really the thing that I want to show you is that when we're talking about our group numbers, they're actually on the periodic table. Now the periodic table, the one that you're using, you printed it from your D2L lab or lecture, chemistry lab or lecture. They should be the same. And what you have here is you have a group number. That's 1A, 2A, 3A, 4A, 5A, 6A, and then 7A. What that means are your group numbers are going to be equivalent to your actual valence electrons. So if we're talking about hydrogen, it's in group 1, right? So how many valence electrons does it have? 1. And we're talking about fluorine, right? Fluorine, if we're talking about fluorine, what group number is it in? It's in 7, which means it has 7 valence electrons. Okay, that's how I'm adding up to see how many I actually need. So let's go back over to our hydrogen fluorine atom. Basically, what I did was I took, if you remember, I took 1 valence electron here, right? And this is going to be represented by a dot. There we go. And then we have our 7, in group 7, valence electrons here. So valence electrons for fluorine are going to be 7. Hydrogen is 1. Fluorine is 7. Now, if you remember, I told you these are represented by dots. So these dots, they connect, right, to make one single bond. So 2 valence electrons that are bonded, 2 bonded valence electrons is going to equal one single bond. Okay? One single. Let's see if I can spell for you guys. That would be nice, right? Erase. There we go. try not to confuse everybody. Know that I am not perfect, and I am not going to restart this video just because it's not perfect. So 2 valence electrons bonded is going to equal 1 single bond. There we go. Got it now. All right. So that's just like a little piece of information that will give it to you. And that's what I'm actually showing you when we're looking right here. Okay. But I want to go ahead and delete this. I'm going to go ahead and erase this only because I don't want to confuse anybody. And I'm just showing you that they're represented by dots. See? So inside this line, you have a dot here and a dot here, and they connect and they form one single bond. Okay, so back at it. Let's just get back on our hydrogen fluoride atom. So basically what you're going to do is you're going to take all of these that you're going to add up. So we have a 1 valence electron plus 7 valence electrons that give us 8 valence electrons total in the molecule, okay? And so what we're doing is, let's go ahead and change our color again, just so I can show you what we're doing is we have 1, 2, 3, 4, 5, 6, 7, and 8. So 8 in our actual molecule, 8 in our whole molecule right here. A total 8 is what we need. So we're doing good on this one, okay? Your molecule can only have this number of electron pairs, and each atom in the molecule has to obey the octet rule. There are actual exceptions for this rule, but we're going to get into those in just a few minutes. But I'll just show you again. Your H atom is in your group 1, so you have 1 valence electron. Your F atom or your fluorine atom is in group 7. That means it has 7 valence electrons. You add them all up. If you take that and you add them all up, you have 8 total, like I said. You divide that by 2, and that's going to give you 4 pair, okay? 4 pairs of electrons, of valence electrons, I should say. Let's go with a V, of valence electrons. And then if we just change the color, because I'm not trying to confuse you, let's go here. We're going to say that this is 1 pair, this is 2 pair, this is 3 pair, and this is 4 pair. There we go. So we're doing pretty good on this one. Feels pretty confident. Your F is obeying the octet rule. The H only needs 1 electron. Remember, it's in 1. That's going to be one of your exceptions to your rule. And we'll get into that in just a couple minutes. Our third guideline that we want to follow is we're going to write our element symbol for the central atom, which is usually the least electronegative. Okay? In HF, let's go ahead and put it all up here. Just throw it up here, get it drawn. Now, you only have 2 actual elements, right? So they're going to both be outer atoms. And that's going to be the case if you only have 2. There are going to be only 2 outer atoms, okay? We'll get into some that are a little bit bigger, and I'll be able to explain it to you a little bit more, but that's where we're going with this one, right? So in the case of the HF, they're always going to be outer atoms because H only forms 1 bond and F is so electronegative, it's only going to form 1 bond. So that's going to take us to our 4th guideline. When we're running in our 4th guideline, we're going to write our element symbols for all the outer atoms around the central atom. So right here, we are dealing with a CCl4, okay? And here, we're dealing with an SiH4. That's what this one is, and that's what this one is. Perfect. So what we're doing is we're going to write our element symbols, and we're going to put typically the least electronegative unless we have carbon. That's what I wanted to show you. So carbon could be an exception. If you have a carbon, it's typically always going to be a central atom. Okay, so write the element symbol for your outer atoms around your central atom. Then you're going to draw a straight line to connect each outer atom to the central atom, which is what we're doing right here, correct? And remember, these are dots. 1, 2, 3, 4, 5, 6, just like you see over here. That's all it is. And we're connecting those dots to make our lines right here. All right, let me just get rid of these dots. I don't want to keep it because I don't want to confuse anybody. And then we will carry on. So these straight lines that you see here and here, they represent a bonded pair. So you're going to subtract the number of bonds drawn from your total number of electrons. Well, let's just go into how many we actually need for this. So if we have one carbon, what group number is it in? And one chlorine, what group number is it in? That's going to be our main question, and we're going to look at our periodic table to find the answer. When I look at my periodic table, it's going to tell me that carbon is in group 4. Ooh, we lost our ability to draw. Let's try that again. Carbon is in group 4, so it has 4 valence electrons. Your chlorine is in group 7, but there are 4 of them, okay? So if we have 7 times 4, we have 28. Let's add the 4 that we talked about from here, which is our carbon, okay? And if we add those together, we come up with a 32 total valence electrons. So let's just count to see what we have, okay? Here, let's change the color. I know we like colors a lot. So we have, this is going to count as 2, 4, 6, and 8. All right, so that's 8. So we can take 8 away from that. And what does that leave us? 24 total. All right, so we're looking for 24 around your outer atoms. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Check. So what we're drawing on this side is right where we want to be. I would challenge you to stop the video and try it with your SiH4 just so you can see how to count them and understand how to count them. All right, so if we go to our next guideline is we have to distribute the remaining valence electrons in pairs, which I just did on the last slide to show you, okay? First, we're going to go around our outer atoms, and then we're going to go around our central atom so that each atom gets that octet. So if there aren't enough electrons for each atom to have an octet, you're going to move a bonding or a lone pair of electrons to share between 2 atoms, which is going to give you a double bond or 2 pairs of electrons shared. And that's what you see with the double dots, and that's why it's actually a different color, right? So you can see these actually go together and these go together. Okay, they're going to bond here. Your electron or your dot, your valence electron represented by your dot belongs to this O, and this one belongs to the O, this one belongs to carbon, this one belongs to carbon. You put them together and they're going to form a double bond. One thing that I really want to make sure that you understand is you're not going to draw double or triple bonds if there are enough valence electrons for each atom to have that octet using the single bonds. So if more electrons are still needed, you're going to move another pair of electrons to be shared and create a triple bond or 3 pairs of electrons. That's not something that you see here, but it is something that carries over from that multiple bonds. So sometimes your central atom may get more than an octet, and this is called an expanded octet. We're going to get into that in just a few minutes. Okay, so one thing, just something I want to add for polyatomic ions, your 6th guideline for polyatomic ions, you should have a common polyatomic ion sheet. It is available to you in your Handy Chemistry Tools content tab that you can print out. Should you print it out and bring it to class, you're going to find yourself in a bonus point situation. So for polyatomic ions, you have to draw square brackets around the entire Lewis structure, and the charge is going to be placed in the upper right-hand corner outside of the brackets, okay? So what you see is you have this is a polyatomic ion. It's a polyatomic ion. They both are, okay? We'll leave it like that.